good morning, everybody. We're going to get started. So thank you for joining the Contribute and Collaborate track. This morning we'll be talking about Docker internals. So we have a couple projects. We'll start with Containerd, then we'll do BillKit, maybe LinuxKit. Our maintainer is not quite here yet, but so hopefully LinuxKit. Then we'll talk about Notary, then we'll talk about Compose, and finally Project Calico. So the way this session is structured is we'll have 6 lightning talks of about 10 minutes each this morning for the first hour, and then we'll break into groups where you'll have the opportunity to ask questions to the maintainers of the project. So we won't be taking questions on stage, but only afterwards when we break into groups. So start writing down questions, and yeah. So Michael, take it away.
All right. So, hi, I'm Michael Crosby. I'm one of the maintainers of Containerd, and I'll kind of go over a quick project status update since last year at DockerCon, kind of what's changed within Containerd and where we're going over the rest of the year. So, since last year at DockerCon, it was when we first started to change Containerd from just the execution side to adding image distribution and snapshotters. And since then, we've hit our 1.0 release, and it has things such as namespaces within Containerd, where we have multiple clients like Docker, Kubernetes, Swarm, all using a single Containerd daemon. And you have namespaces so that you don't have snapshot or container ID collisions among all these clients consuming the underlying runtime. We got snapshot support in, which is kind of the V2 implementation of graph drivers, if you're familiar with that from Docker. We have various ones like Overlay, BetterFS, ZFS, and AUFS. And then we got push-pull in at this layer and general performance improvements around that. And we also improved on various things along the runtime of container metrics. We export everything via Prometheus now instead of like a HTTP stat API. So you can aggregate all container metrics on the system as a whole and collect them in one go. And then you can use all the Prometheus labels to filter on, was this container launched by Kubernetes? Was this one launched by Docker? What's the cumulative memory usage of all Docker containers versus Kube containers? Things like that. So we think it's a pretty good stats API for kind of where we're sitting in the stack now. And with 1.0 is our stability and backport guarantees. So we've had various point releases that haven't introduced any breaking changes along the life of the 1.0 branch. And kind of we'll continue to be doing that. With 1.0, we've also did a lot of testing, and this is a little output from really ugly stat or stress test server, and we run about 4 million containers every 5 days on the stress test server and over 1.6 million exec processes, and it just runs constantly every day, all day long. When changes are pushed to master, every hour it pulls in the new build of Containerd and keeps running stress tests and things like that to catch regressions or even performance regressions, because performance is really important to us in Containerd. So moving on from 1.0, we just released 1.1 with Kubernetes CRI support, and we initially had a separate project called CRI Containerd, which had the CRI endpoint. And with Containerd 1.1, we moved that CRI endpoint into Containerd, so you no longer have to manage 2 separate servers to get Kubernetes to work with Containerd. It's you run Containerd, Docker can connect to it, Kubelet connects to it, and you don't have to worry about anything else. So along with that, just this week, Google Cloud announced that Containerd is the default on GKE alpha clusters. And you can read the blog post here I linked, and then the initial blog post of when we finished the CRI Containerd work around a month ago, I guess. And that kind of goes into detail how the model works, how our CRI implementation works within Containerd. And then finally, kind of like what we're working on, where we're going over the next year or so. We've been doing a lot of work with GPUs at the runtime level. So just this last week, we got NVIDIA GPU support merged in Containerd. And kind of the next steps for the Docker stack is pushing those APIs up from the runtime level into Docker and its users. Still been working on checkpoint and restore. It's been kind of like my multi-year project that I've been working on, but the latest kind of advancements with live migration and stuff within Containerd is it's always had checkpoint and restore for years now, but it would checkpoint to a directory and you would be left on your own to move that directory with the memory data to another machine and restore it. And with Containerd 1.0, we checkpoint to an image that you can push to a registry, pull down on another machine, and restore your containers there. And it not only checkpoints memory, like the live processes in memory, it also checkpoints the RW layer of the container so that can migrate across hosts with it. And then we have things such as Windows support that we're getting in, and then working on hypervisor isolation. So gvisor, Kata, things like that is our other push. So I'll show you a quick demo, which is pretty different from a lot of other Containerd demos that are usually Linux. This is Containerd on Windows. And so we have a containerd.exe. I can run that. It boots up just like it would on Linux. And then I can go into another PowerShell. We have pool, so CTR, my internet's down, but CTR is our development tool within Containerd, and you can use it for testing things. Our main supported client is the Go client that CRI, Docker, everyone consumes. But for demo purposes, I'm using CTR. And this is running Windows containers on Containerd alongside Linux containers. So that's kind of all I have as a project update for Containerd. And then if you have any questions, we have that area over there later on. So thanks.
So I'm going to quickly cover BillKit and also give you an update of what's happened in BillKit since we last had this SIG session. If you're not familiar with BillKit at all, then it's this open source project that we created under Moby to basically reboot the innovation around Docker build. It's a completely fresh take of what we think a modern container builder should look like, what it should do, things like that. So it fixes a lot of fundamental issues we had with current code base. It has lots of performance, and I think most importantly, we think that BillKit is an okay platform that we could use to continuously innovate on Builder now, continuously push updates and add new features. So the biggest update we have in BillKit probably is that we are bringing BillKit to Docker daemon. So previously, if you wanted to use BillKit, you would have had to use the standalone version or use it with in combination with Containerd. Now, in the next version of Docker C 1806, you have a possibility to use BillKit directly when you're running Docker build. It's experimental. You need to opt in. I will show you this later. And I think we'll just go straight into the demo and see how this thing looks like. So I'm in this demo machine in here. I have Docker installed in here. There's nothing in here. It's a completely empty box, no build cache or anything like that. And I'm in a project. It's the movie code base. There's a Docker file. If my internet comes back. Okay, there's a Docker file. Very complex Docker file, lots of stages, things like that. So, and what we can do now to build this with BillKit is we have to opt in. You opt in by doing export, and you set this environment variable Docker BillKit to true. And once you do that, then you can just regularly do Docker build and dot, or let's do something different. Let's not wait for all of this big Docker file to build. Let's just build one of the stages. So we can select a stage like you do normally with -s target. I know that there's a Docker CLI stage happens to be in here. So let's build this stage. And you can see is that the BillKit output, you can see all the steps that ran as part of this build. You can see that BillKit was smart enough to not run everything that was in this big Docker file, but only figure out what actual steps were required to building this stage. So it's much more efficient than the current one. You also see that when we transfer the build context to the daemon, then the build context is like 1.5K, and you can believe that like Docker code base is much bigger. It's like more than 100 megs. So BillKit was also smart enough to see that this stage didn't really use all of those files. The Docker file only used a couple of the files, and when it transferred the build context, it only transferred those couple of files, and it was much faster because of that. What else? We can just run it again. You can see that it's of course cached now. It's almost instantaneous. What we can do else is, well, let's see what happens when I built the whole thing. So this thing had lots of stages. So, and now you can see that the transfer context was bigger, and you can see that lots of things are now building in parallel. So there's like 10 things are building in parallel at the moment because BillKit can figure out that those stages that are required for this build don't have direct dependencies. They can be built parallel. It's much faster this way. So let's not wait for this to finish. It takes like 2 minutes. Let's cancel this and let's see one other use case we have. So exactly the same thing. I mean, I switched to a new box in here that's also completely empty, no cache or anything, no images. And here I'm in BillKit's own code base. Again, very similar situation. There's a big Docker file, lots of stages. Probably the most most complicated Docker file you will ever see. So if I would just build it now, it takes like a couple of minutes. But what I did yesterday is that I already built it, and I used BillKit's remote cache feature to actually push the cache that this previous build made out to the registry. And now I can use let's do cache from. Now I can build with Docker build with specifying the cache from flag, and I can just reference this build cache that I pushed earlier. And this is just like a build cache that lives in Docker Hub in this case under my account. This is the name of the image. And so I'm now building from empty state using a remote build cache, using this complicated Docker file that has lots of stages. And in the end, it will use multi-stage builds to make this really small image. So let's see what happens now. So you can see some of the things that, well, you can see that it finished. But what you can see as well is that it imported this build cache from here, and then it used this build cache or the metadata in this build cache to figure out that everything I have locally actually matched this build cache already. So it followed all the stages, figured out that even the last stage would be the same, even the last minimal stage would be the same. And basically the only thing that it needed to do is pull the cache for the last stage, and it was super fast. It took like 3 seconds. So, and if I do Docker images, I see this this image here. So basically, the speed of the build was more similar to the speed of the pull. And of course, you may say that, well, how often are you going to have exactly the same cache that you used previously? So let's see what happens when I just do an update in here. So I just going to do like a dummy update in one of the source files. And so what this should do is it should rebuild my local binaries, because I'm building from a local source. This cache is not valid anymore. So if I run this thing again, you will see that it now picked up that some other point from this graph still made the cache match. So when this helper dependencies were installed, it still made a cache match, but not for those binaries. So it specifically excluded those 2 steps. It's rebuilding those 2 steps, but everything else is still cached. So when these steps will finish, you will see that it actually, for example, this build also builds containerd and runc. So the containerd and runc were still cached because I only changed code for some of the binaries. So this would probably be very helpful for for example, CI systems. You run the CI, you export the cache. Next time you run the CI, you have the cache from the previous run, or cache from the master branch, things like that, and you only need to rebuild stuff that actually changed. So let's go back to the slides and give some more quick updates. So as I showed you, it's in Docker C now, or it will be in the next version. It's available in nightly build at the moment. There's some other projects that have started using BillKit. We have an IMG builder that is like a standalone, unprivileged version of a builder that uses BillKit under the hood. OpenFast Cloud uses some nice combination of serverless and image building using BillKit. And we have there's a project called Container Build Interface that's allows you to use Kubernetes YAML to start build jobs, and it also supports BillKit. So these were the integration points. Let's see what's new in the standalone version from the last time. I already showed you we have finished up the remote build cache thing. Seems to work quite well, in our tests. Then we now have support for rootless execution. So if you do a little bit of setup, you can start BillKit with a regular user. Thanks to Akihiro Suda for a lot of work on this front. Then, as your builds get more complicated, you need better visibility of what actually happens during the build. So in BillKit, we have open tracing support from client to the daemon. You can see how they interact, how they exchange data, what steps are parallel, things like that. Gives you a nice overview of everything that's happened inside. And something that's a little bit work in progress at the moment is that we are working towards the multi-worker model. So we can't fully do distributed builds yet, but you can already set up start the BillKit daemon with 2 workers and switch between them and things like that. So this is definitely the area we're looking into. And some of the Dockerfile updates that I quickly mention, like I showed you, we can now do the automatic context detection. So we look at the add and copy commands, see what files you actually use, only transfer those files. We still do the change detection as well. So if you're doing a repeated build, we only send the files that changed. And we also have this new syntax directive that I don't have much time to cover, but what basically allows you to use the remote frontends feature in BillKit to dynamically load in implementations of Dockerfile features from an images in a repository. So as a showcase, we have implemented this run-mount proposal that allows mounting files directly from other stages and build contexts and allows doing like application-specific cache. And unfortunately, I don't have time to demo it at the moment, but you're welcome to come to this talk later today, where we will have a little bit more time. I'll cover some more internals of what's happening inside BillKit, how it's implemented, and also I will demo the application-specific caching, run-mount, syntax directive, things like that. Just some topics I wanted to point out for the later POF session. So come and ask questions from the maintainers. Maintainers are in here. Whatever questions you have, we will try to answer, or if you have already feedback and things like that. There's also some of the topics that we will probably discuss that are kind of an open questions at the moment, like what do we do with build secrets and privileged executions. Seem like hot topics. And that's it. Just want to thank you all the maintainers and people who have contributed to BillKit. And please check it out. Check out the 1806 version. Opt into BillKit. Try it. Provide us feedback so we can bring it out of experimental soon. Thanks.
Okay, so I'm just here to give you an update on LetsGet. So in case you don't know what LetsGet is, it's a toolkit we built for building whole Linux systems that's built on the same kind of basis as Docker itself. Everything's built from containers. With containers, everything runs in containers. It runs on Containerd. We were one of the earliest users of the Containerd 1.0 series, and we've been dogfooding all the way along with the new releases, and with the CRI support as well. It's designed to be fully customizable and fast, and it's designed like containers to be built in a CI pipeline for building your whole system. In terms of the CNCF landscape, we fit in with tools like Puppet or other host configuration tools, but LetsGet's very different in sort of look and feel from there because it's designed for building immutable systems rather than mutable systems. So it's designed in a way the most similar tool that people are used to using is Packer, but LetsGet is much. I'll show you a little demo of how the feel for it in a minute, but it's much simpler to use than Packer and much faster. We launched a year ago at DockerCon 2017, so just over a year ago, and it's been a really productive year. We've had a huge number of contributors. We've got over 100 contributors. Most of them are not Docker people at all, and they've contributed all sorts of support that's been really valuable, and we know that they're using it for really interesting things. For example, we had ARM64 support and IBM contributed S390X support, so you can run LetsGet on your mainframe and your ARM server as well as your normal x86 servers. We have support for running on loads of easy support for loads of different cloud platforms and bare metal platforms, and people have contributed all sorts of helpful fixes, improvements, documentation, all sorts of things, which has been really valuable. Our primary initial use case for for LetsGet was Docker Desktop, where we have, as I said in the keynote yesterday, we've added over 1 million users in the last year. These are people who are using LetsGet without realizing it. In general, it's just an internal hidden piece that's invisible. But we make use of the Kubernetes support, which we built for LetsGet, which we demoed a very early version of at DockerCon last year. And we now use that to build what's now a certified Kubernetes distro for desktop, which is a really easy way to do that. And that was, again, the work on the Kubernetes distro was originally a community contribution from Weave, and lots of people have helped us build that, and it's a really easy way to run Kubernetes. We have support for running it with Containerd with 1.1 with the CRI. There's a bunch of different build options in the repo, so you can try out. We've been using it to test out the Containerd support for Kubernetes as well. Other use cases, lots of people do use it for Kubernetes. We've got some really interesting work with IoT platforms. We're working with Microsoft and Linux containers on Windows support, which is using LetsGet as the build system for building the Linux images. And we know there's lots of other people using it in production, but in many cases, we don't actually know exactly what they're using it for, which is great. It's one of those projects that people just take it and use it in lots of different ways, and sometimes they contribute things, and we hear about their use cases, and sometimes they don't contribute things, which is great as well. I'm sure there's people here who are using it in lots of interesting ways that you can talk about. The things that we're really planning to work, one of the things we really want LetsGet to build without Docker. The real reason for this is because building in the CI pipeline is a really important use case, and people don't always have ability to spin up VMs and install Docker. It's really kind of inconvenient, so we'd really like it all to be buildable with a single Go binary that runs natively on any platform, which would also make it faster. There's quite a lot of work, particularly around writing file system code in Go, because it's difficult to construct Linux file systems at the moment without spinning up a Linux VM. But we're pushing away at that. Avi's done a lot of work, and we're hoping to ship that soon. We're also going to integrate a bunch of the work from Containerd in terms of the actual file system extraction and so on. So it's a lot of work, but it's really helpful to make it even more invisible and easy to use. We need to switch all the disk formats using SquashFS. We've kind of spent a bit of time on image formats, but people are using larger and larger images. Originally, when we built LetsGet, it was we were building very, very small images because we were largely running Docker. When we started building things like Kubernetes, which is much bigger than Docker, the kind of init ramfs model we used to use has started showing its problems, and it's kind of annoying. So we're going to switch all those over. There's some prototype work on that, which should happen soon. I'm doing a talk with Luke, who's over there at 110, which you should come to if you're interested, about managing persistent storage in LetsGet. So you can snapshot and restore the state. So you have an immutable system for your code, and then a mutable state that you can transfer from one machine to another, from one cloud server to another, from cloud server to bare metal, and restore the whole state of the machine, snapshot it, and manage state in a way that works really nicely with immutable infrastructure. And this has been a really interesting collaboration, and it's a really nice way of working. I'm going to show you a quick demo. This is kind of, I think this is just a basic, simple workflow. We basically, the whole idea of LetsGet is it just should be making Linux for some use case should just be really quick. But I didn't pull my images before I did this, and I updated it, so it's not going to be immediate on this Wi-Fi. I think I've probably got it. It'll build in a second, but it should be. The rest of it's all locally cached or pulling a little bit quicker. But the whole idea of it is you can just build Linux distros in the same kind of way as you can build containers. So everything is just, if you just want to experiment, if you want to spin up thousands of machines on any platform in a reproducible way, it's really, really straightforward. And then we can run that, and it boots up a Linux machine. This is running locally on my Mac, and it's spinning up containerd. So it's really, really fast and straightforward and easy to iterate, and gives you a platform that's really simple to use. So we got it, and then we can dispose of our machine. So thanks very much.
Hey everyone, my name is Nassim. I'm a security engineer at Docker, and I'm gonna talk through the main security features that we are working on, and like a quick update also on on Notary and what is going on right now. So on the Notary side, what's happening is basically adding support for the CouchDB as a backend for the server and the signer storage. So right now it's using RethinkDB to store everything. The main differences are that CouchDB will allow people to connect to the if it's using the cloud version of the CouchDB, basically a different authentication mechanism. You can do it either through a certificate or a username password. But yeah, it's basically using it's using the same mechanism as the current RethinkDB driver for the storage. We are also work in progress for the Notary import and export in order to import and export trust data and files, so either files or complete repositories, in order to clone your repository if needed. We are also adding the ability for people to plug their own signing services. This is a big need for plenty of enterprise customers and users who already have their own signing service in-house and don't want to have to re-audit everything. So providing an API to do this was necessary. There is also a security review that is going on thanks to the CNCF. As most of you may know, the Notary got accepted into CNCF, and so part of that is a full security review of the project. And we also added the ability not to dump the service. The signer service memory through ptrace, which was pretty important. So yeah, that's pretty much what's going on the Notary end. The integration, the Notary integration inside Docker is called Docker Trust. I hope some of you use it. It's integrated into DTR, so we have end-to-end testing on that. It provides a higher level of abstraction in terms of trust management, so that you don't have to think in terms of delegations and targets, but more into actual files and signers. One of the big downsides at the moment is that we don't really tie signers identities to Docker logins, and on the long term, this is something that is pretty mandatory if we don't want to confuse users. What's currently available on Docker Trust? So we have a few features: the ability to generate keys, load keys, adding and removing signers along with these keys, and inspect the trust data as well as revoking it when you sign images. The goal is to be able to implement a full abstraction on top of what Notary does as of today. So all the additional key management commands need to be implemented. The ability to rotate keys, change the passwords, a lot of inspection features, and also the ability to pin public keys onto certificates and so on. And yeah, visibility is pretty important. Users, as of today, don't have the ability to inspect what is going on their trust data, and that's also like something that is mandatory for people who care about security. So as of today, they have to use Notary to do the actual like key inspection, listing what is going on, what are the keys available on such or such trust repo. We are planning to add a second level of improvements, some sort of redesign, so that you can actually potentially manage groups of signers together, so that it fits more into the user management level that you have on other tools out there. Managing groups of signers is something that's pretty important at scale. And the idea is to provide the friendliest signing tool, signing and trust management tool possible. So having the ability to specify signing policies onto images, specifying all who are the, let me show you by the way, it's going to be a little bit simpler. Yeah, quick sneak peek. It's a work in progress, but yeah, basically the idea would be to add a bunch of commands to create groups, to create signers as part of groups, a little bit in the in the Unix style of managing different groups and so on. So yeah, that's basically the idea. Also, the ability to manage policies onto complete repositories or for organizations or images, so that you can say, hey, I have, for example, I have 10 people who are allowed to sign this image, but I would require at least 4 to bless it, so that it can actually be deployed onto production. So yeah, that's a lot of work that's going to be done on top of Notary and inside Docker Trust itself. So stay tuned for that. We also have a more recent security feature that it's still work in progress too. It's called the Docker entitlements. I'm gonna mention where it's at in the Moby, which part is closed source, which part is open source. The idea behind this feature is to provide simpler level of abstraction regarding security permissions that you give to your containers and services. People right now have to dive into all the kernel capabilities. How do they interact with the namespaces, with the Linux security modules? Everything at the kernel level is exposed as is to the end user, and it's just not possible for them to make good decisions. And most of the time, if they see something that is blocked by the default universal default second profile, AppArmor profile, etc., they generally opt out of the security rather than trying to find out what is going wrong, even for images that contain a pretty clear documentation on how to run the image. So the idea would be to first specify a set of permissions that are really easy to understand inside each category, giving a level of permission. And yeah, the platform behind the scene would translate it into its own understanding of the meaning of this thing. So maybe Docker has a certain understanding of what it means to be network accessed, to be confined on the network access. Meanwhile, other platforms would understand it in a different way and would be able to translate it into their own container level settings that they are generating and using to run the container itself. So, and the other idea would be to provide the entitlement very seamlessly to the end user, so that they don't really have to specify every time what they need to run the application, right? This is still, even if you provide the set of entitlements needed for an application, the user may be lazy, which is understandable, and might make the wrong assumptions or decisions in the process. So the idea would be to actually leverage the knowledge that the image, the people who build the image have on the image itself, so that the person running the image itself has only one decision to make. Basically trusting or not the content publisher for this image. So building the entitlements inside the image to create some sort of image with its own security profile, having it signed so that when you receive an image, you know that it's actually created by the exact entity that you plan to specify your trust on. And when you run the image, you would only have to specify this. So the user experience as of right now is pretty bad at the security decision making level, and this is one of the key features to improve it. We also don't allow easily developers of applications to specify to give us knowledge on the application itself. Most of the time it's documentation, so that would help a lot. And yeah, removing everything that allows users to opt out so easily out of container settings, container security features such as SecComp, AppArmor, etc. And yeah, the idea would be to improve a little bit the least privilege principle, rather than having a universal security profile that basically matches 99% of the needs out there, and hence not being as secure as it should be. The base mechanism for this is available, is open source. It's available under the Moby umbrella in the lib entitlement repository. Feel free to check it out. It basically contains an entitlement manager and the current entitlement implementation. So entitlement being each one of the permissions with its own translation into OCI configuration, OCI level configuration, and AppArmor profile generation, etc. So you have like a full AppArmor profile generator inside the repository, for example. Feedback is of course more than welcome. This is a very hard problem to tackle, and it will be very hard. Yeah, it will be very hard to fit everyone's needs. So feel free to provide feedback. And yeah, the idea is just to build like profiles for the most pulled images. Thank you, everyone.
Hi, everyone. My name is Joffrey. I'm the maintainer of Compose and Python SDK, among other things, at Docker. Apparently, I missed the memo that we're all supposed to give an update, so I'm not giving an update. This is a plea for you to like migrate from version 2 of Compose to version 3 of Compose. And to some of you, that might be old news. You're like, oh, I'm already using v3 for like years now. But you'll be surprised, like 25% of the new Compose files on GitHub in 2018 were still on version 2. So I'm gonna just like go through 3 steps here, like why do you want to migrate, what are the applications that you can upgrade, and conversely, what are the applications you can't. And the third part is how to proceed and like the common migration challenges that you may encounter. So before I begin in earnest, I would just want to say this is kind of general purpose advice. That's what I can fit in a lightning talk. I might not address all the use cases. I'm happy to talk more after this if you have things that I'm not covering here. So let's start with like why do you want to migrate? And I think it boils down to 2 reasons. The first reason is v3 is like this cluster ready. It's been designed to work with swarm modes originally. Now, if you have Docker Desktop or if you have Docker Enterprise Edition, it also allows you to deploy on Kubernetes with Docker Stack Deploy. Additionally, it supports secrets and configs, which are ways that you can like inject things like passwords and API keys and everything into your applications in like secure ways. So this is like a really great upgrade in that sense that it really allows you to like go to the next level in like distributed applications. The second reason is I think it's time. It's been the standard recommended format for a while now. We introduced version 3 at the end of 2016. The format has definitely matured significantly. Like 3.0 was like a little bit first draft, but we have 3.6 now, which is like really like has a lot of the features you want and is a really good format. And version 2 will eventually become deprecated. The new tools that we're like working on right now inside Docker are not like, we're not looking at supporting version 2. So it's it's time to upgrade. So yeah, let's go quickly over like what can be upgraded. Those are like the no-brainers. If you have like traditional web apps with like front end, back end, like your LAMP stacks, your like Python, like Django web service plus like Redis plus MySQL or whatever. All that stuff is like super easy. The microservices, same thing. Everything that's like online APIs, daemons, that can all like be migrated pretty much seamlessly. There should be like minimal challenge. Those are the things that you can really do. So everything that's like host dependent, if you have things that are like specifically designed to like modify the files on your machine, if you want to use the like host network mode, that kind of stuff, it's kind of specific. But yeah, it's like because v3 is like designed to work in distributed environments, probably v2 is still the best way to do those things. For the apps that need like additional kernel level permissions, everything that's like privileged or capabilities add, that kind of stuff, it's a work in progress. We're going to add it in v3, but it's not there yet. So that's not ready yet. And finally, the build jobs. I'm going to like explain this a little bit better later. But what I want you to understand is that ideally, Compose is not the right tool to do this either. Finally, there's like one thing that is kind of a maybe. I've seen that a lot from on the Compose repository, where people have like their regular application stack, and they add in their Compose file a service that just runs tests against the thing. So this is like, V3 is not like super good for that if you're using it with Docker Stack Deploy. I think we need better tools to do this. I'm happy to like discuss this more in detail if people are interested. But it's possible, it's just like not a great experience right now. Okay, so how do we migrate? There's like the trivial stuff that I'm not gonna go over because we don't really have time and it's not interesting. Everything is in the documentation, like the property names that change or move or stuff like that. You can go over. One of the most common challenges I've seen is people struggling with service dependencies. As you may or may not know, the depends on option is ignored when you deploy with Docker Stack Deploy. In most cases, actually, this is not really a problem because the default restart policy for services is to restart until they can actually like stay up and everything. So your app will come up eventually once your database is ready and whatever. That said, if you have control over your application and you can write the code yourself, it's really a good idea to actually handle that kind of like connection blips and everything inside the application, because it lets you handle not only the startup, but then everything that comes after, like if a physical machine comes down or if there's like a connection issue or whatever. I think that's important. So yeah. The second thing I've seen a lot, at least on the Compose repository, is people miss volumes from. So this is not good. This is not in the V3 format. As far as I can tell, it's often used with like one service that generates files or generates assets in some way or another, and then it's fed into like other services using volumes from. So in version 3, like the advice we have is to actually extract this from your Compose file, make it a separate task. This is because it's better for separation of concerns, and it better reflects the distributed nature of Compose in V3. So let's just like step back a little bit so I can explain better what I mean by that. This is the typical like deploy lifecycle in my mind. We start by like building images, push those images to the registry. Then we go to our deploy environment. We pull the images which is pushed, generate the pre-deploy artifacts, which are like the typical like volumes from thing. Deploy to the cluster, and then do the like whole like monitor like runtime lifecycle thing. Some of those steps might be optional. If you're like developing on your own machine, you don't need to like push and then pull again, obviously. So the thing is, Compose is actually designed to do this thing here, and not all the other things. But obviously, when all you have is a hammer, like everything looks like a nail. So that's kind of a problem we've had. Is Compose is kind of like the like front end tool to like manage like multiple multiple services and everything. So I totally get it. So I want to introduce a few new tools. One of them is an experimental tool that we've been developing at Docker, and we actually open sourced yesterday. The other one is a tool developed by someone in the community. So the first one is Docker app. If you've been at Garris's talk yesterday about Docker for developers, you might have heard of it already. If not, I totally encourage you to like check out the blog post and everything, and check out the GitHub repo. It's the idea is to be able to like describe a Docker application like kind of beyond the set of services, like as an application package, and like having the ability to like version it, deploy it, distribute it, and make that a first-class citizen of the Docker ecosystem. The other project that I want to introduce you to is called Dobby. This is more of a build automation tool for for Docker applications, and it's a little bit like it lets you like write a YAML file that's kind of like a makefile, but for a container world. That's all for me. Thank you for listening. I'll be like around here. We can talk about all the different things I went over and more later. And thank you.
So we have one more talk on Calico right now, and we also have lunch in the back, so no need to go all the way down. So when we break into groups for more informal discussions, feel free to grab lunch at the same time.
All right, I'm cogent of the fact that I'm standing between you and lunch, so I'll try and get through this fairly quickly. How many people here have been using Kubernetes and Docker EE yet? How many people are interested in networking in Kubernetes and Docker EE? All right, so at least some of you will find this, hopefully, somewhat interesting. I'm Christopher Lilienstolpe. I'm the CTO for solutions at Tigera, the home for Project Calico. I'm also the original architect for Project Calico. So anything that you like about it's my fault. Is you can give me credit for. Anything you don't like about it, it's the engineers that implement my architecture correctly, and you can blame them. So Kubernetes network assumptions. I'm just going to go over really quickly how Kubernetes views networking, which is maybe a little bit different than the way Docker Swarm views networking. One of the assumptions is that all containers or pods in the infrastructure should be able to communicate with one another without using NAT. They should all have their own IP address. And two, the IP that a container sees itself as is the same as the others see it as. So again, there's no NAT. Everything should have its own address, and that address should be unique across the fabric. So the way Kubernetes does networking, much like Docker has CNM, Kubernetes and a number of other platforms use something called CNI, Container Networking Interface. The way the Container Networking Interface works is that the kubelet, which is the agent that sits on every worker, when it has something to do in the network, it makes a high-level request, and that request is something along the lines of connect this pod, disconnect this pod, etc., to using the CNI plugin constructs, which get passed to a CNI plugin library and something that exposes that. In the case of Project Calico being the batteries included networking for Kubernetes and Docker EE, that runs on every host as well, and that picks up that message. And the CNI plugin takes care of doing the networking work. So pretty much everything's just handed off to the CNI plugin to do, and that includes things like IP address assignment. So there are three things that Tigera's CNI plugin does from a networking standpoint. We also offer network policy, and I'll talk about that in a second. So we do the IP address management for all the pods on the infrastructure that are launched under Kubernetes. We handle all the on-host networking. How do pods talk to one another on the host, and how do they talk between hosts? How do pods on different hosts talk to each other, and how do you ingress and egress? We also take care of network policy. So this is different than, to a certain degree, from Swarm, in that we do not use network constructs like separate overlay networks to isolate traffic. And we can talk more about why that may or may not be a good idea, but if we think about in a microservices architecture, where we no longer have mainly applications that sit in a silo, north-south, it's hard to say this thing is going to be part of application A and this thing's going to be part of application B, because this thing is maybe offering services to A, B, and C. So now how do you, if you're going to put this in application A's network stack, how do things from B and C access it? You then bring in firewalls, and I'm sure we all have lots of fun with firewalls and getting firewall rules pushed through. Calico takes a very different approach, and Kubernetes, to a certain degree, takes a different approach, in that the networking is separated from network policy. And instead, we have a construct called network policy where you basically define what can talk to what. And the way that gets rendered is different from for each plugin. The way Calico does this is we actually do filtering right in front of the workloads. So you can use this for something very coarse, like stage tier separation, dev test prod, tenant, Coke can't talk to Pepsi. You can use this for true microservices segmentation. This front-end application can only talk to these back-end applications, and these back-end applications can talk to these sources of data. We can also use this for compliance. Workloads labeled PCI can't talk to workloads not labeled PCI. So you can use this for compliance as well. The way network policy works, Kubernetes is very metadata based. So you attach labels to workloads. Those labels aren't just used for networking. They're used for a whole sort of other things. You can use that for labels that are used in Kubernetes to identify what storage you might bind to, what services you expose, what load balancers you attach to, etc. Metadata is used for a lot of things. We leverage the same labels in network policy to identify policies that will affect a given workload. So you can say workloads that are PCI compliant are labeled PCI compliant, and then you can have a policy that says any workload labeled PCI compliant will only accept or send traffic to other workloads that are labeled PCI compliant. Or you can say workloads that are in stage dev can't talk to workloads in stage prod. So that's this pod label selector, and I've got an example of that in a minute. We can also use the namespaces in Kubernetes as labels, and you can match on protocols and ports if you really want to. The interesting thing in Kubernetes, the minute you attach any kind of policy to a workload, that workload is isolated. So if you attach a policy that attaches to all workloads, for example, in a namespace, at that point, those workloads can't talk to anything other than what policies say they can talk to. So the minute you apply policies, you are in a default deny situation. And then you add what you can talk to rather than the other way around of constraining. This requires a controller to implement. So Kubernetes has this great model. They don't have any code to implement it. They rely on those network plugins to do that. And Calico has a plugin. We are sort of the standard implementation in Kubernetes for network policy. So this is an example of a network policy. In this case, what you can see is you give it a name, you identify what namespace it runs in. Calico can also do global policies. That's an extension on Kubernetes policies. You can write a policy that spans multiple namespaces in Kubernetes. In this case, there's a pod selector. It says this policy will attach to anything that's labeled role DB. And what this policy is going to say is I'm only going to allow ingress traffic from things labeled role front end on TCP 6379. So in this case, in the my namespace, anything labeled front end can only talk to things labeled role DB on 6379. And unless there's any other policy, this role DB won't be able to talk to anything else. A couple of other things in Kubernetes is an allow all model. If you go to Project Calico's extended, you can also do allows and denies. So you can do denies as well as allow policies. This is a little bit of the architecture real quickly. It's distributed, just like Swarm's built, just like Kubernetes is built. We have agents that sit on every node. We have no global controller. Basically, what we store in the key value store is information about what's in the network and what the intent is. DB can only receive traffic from front end. And then this agent, which sits on every host, watches that key value store. We use etcd or Kubernetes itself, and makes a determination if it needs to make any local changes on the host to render that intent and connect those workloads. So workloads hang out here. There is no switch. There is no L2 connectivity. This is always routed. We're using the Linux kernel as a router. And then we install firewall filters in front of each and every workload to enforce that policy. If we take a look at how these things are built, this orchestrator plugin is a CNI plugin in the Cube controllers. These are what we talk to Kubernetes. These things are distributed across the infrastructure, the actual CNI plugins on every host, and there's some number of Cube controllers, and those are listening to the network policy API messages. That gets written into etcd in Docker EE. This is etcd. This isn't Kubernetes' data store, it's etcd. The other, actually I drew these lines incorrectly. The orchestrator plugin are the CNI plugins, and that's what I get for cutting and pasting. Forget about this line. So these are the Cube controllers and CNI plugins. Down here on Calico node, this is the CNI plugin as well. That's sitting here. And then we have something called the Calico node container, and that runs Bird, which is a BGP daemon. That's how we talk to the rest of the world about routing information, and Felix, which is the thing that drives the Linux kernel. There's nothing we install in the kernel. This is all standard Linux, etc. I can walk through a pod lifecycle if people are interested, sort of how things get spun up. Would that be of interest on what happens when a pod shows up in the network? Okay. So start off with a baseline Kubernetes environment. You've got a Kubernetes API server over here. That's something you can listen to for events for Kubernetes. You've got the Kubernetes scheduler. You've got controller managers. And on each workload, on each worker, you've got a kubelet. Pods, the Kubernetes scheduler tells the kubelet to land some pods. Those pods get instantiated on the workers. This gray box here is the Linux kernel. Every time a pod shows up, the kubelet asks uses CNI to ask for networking for those pods. In our case, there's a configuration file standard configuration file that tells the kubelet what CNI plugin to talk to. In our case, that's Calico CNI plugin. That also has an IPAM capability. At that point, the CNI plugin will attach each of the pods to its own virtual interface, which is connected to the kernel. So everyone gets a unique interface. And then the IPAM function will assign an IP address out of a larger range that you've given to Kubernetes, said this is the address pool or set of address pools for your pods. We then assign addresses appropriately to those workloads in the pod itself. So the pod knows what IP address it is. No DHCP is used in Kubernetes. Once all that work is done, the CNI plugin tells etcd that work has been done. So now everything in Kubernetes knows where those pods are, what interfaces are attached to, and their IP address. etcd will then turn around and tell the Felix agent, which we have running on every host, that there is a new pod, here's its address, and here's its interface. Felix will then take those IP addresses and install them in the Linux kernel routing table. At this point, all the pods on a given host can talk to all the other pods on a given host. If you trace route between two pods, you'll see a router hop in the middle of it, and that's the underlying Linux kernel. Once those routes have been installed, the BGP daemon wakes up, and in the way Docker EE, the way this works, is the only thing we're pairing with is other nodes. We're not pairing with any other infrastructure. We have lots of people, though, who pair us with, say, top-of-rack switches, etc., and they actually integrate us into the underlying infrastructure. But this routing daemon auto-configures itself, and it then picks up these routes and advertises an aggregate of them to all the other pods, to all the other workers. So in this case, the routes get propagated. We know this works. This is the routing protocol that drives the public internet. We know this works at scale. If you have a cluster that's bigger than the public internet, I'd really like to know about it, but we're pretty sure this is going to work at scale for anyone. And then we install the routes we've learned from the other workers into the local worker. And now all the pods can talk to all the other pods. And that is where, and then we go through and we do the route filtering, the security policy enforcement at that point. And that's another set of walkthrough. Only other thing I want to talk about real quick is networking constructs. By default, Calico does not use overlay networks. We do not need to use overlay networks. However, Docker has decided by default on Docker E, they want to use overlays so it matches the behavior of Swarm. So by default, we have an overlay, very lightweight overlay mechanism called IP and IP. It's an IETF standard. And just like any other overlay, so today, if you just turn on Kubernetes and Docker EE, you will have an IP and IP packet for traffic passing between two workers. And the way it looks is fairly obvious. It's an IP packet with another IP packet. However, that can be modified. That can be changed. So we have 3 modes for IP and IP. By default, in EE, it's always on. If it's off, then all traffic, we've got an example here. We have 2 workers on the same subnet, another worker on another subnet. One of the workers on the first subnet has 2 pods, one has another pod, and then the worker on the other subnet has another pod. In the case of IP and IP being off, there is no encapsulation used for any of these connections. On the same host, there's no encapsulation. Between hosts on the same subnet, no encapsulation. Between pods on different subnets, no encapsulation. If we go to always, and this is the way Docker has it turned on by default, there's no encapsulation within the host. Between any other workers, there's encapsulation. So there's encapsulation across in the same subnet and across subnets. One place where we do see IP and IP used fairly commonly is in places like on Amazon across AZ boundaries, where the routers, Amazon doesn't really let you talk to their routers all that well, effectively. So in that case, we have a mode where we only encapsulate using IP and IP when we cross a subnet boundary. So in this case, everything on that one switch that's in the same subnet, there's no encapsulation. When you go across between 2 subnets, then we encapsulate. So those are the 3 modes of IP and IP, and that's a 1-line config change. And you can change the behavior of encapsulation in your Docker EE Calico installation. This is how Calico is installed in Docker EE. You have the standard Docker EE infrastructure. Then we have everything that's managed by Swarm. And that includes all the stateful things like the auth store, the etcd key value store, etc. All of those mechanisms are managed. Everything in teal here is managed by Swarm, including all the Kubernetes master components. Then, that was unfortunate. Then, Kubernetes deploys Calico, and that's the purple nodes here, the purple boxes here are the Calico components that are managed by Kubernetes. And they have, when they need to store state, they're talking back to this distributed key value store, which has been managed by Swarm. So this is how the system gets built up as it deploys. That's it. I'll not keep you from your lunch any longer. I'll be sitting at that table over there with a whiteboard if anyone wants to get into the deep and gory details of networking, network policy, etc. Thank you.
All right. So please join me in giving one more round of applause for all the speakers this morning.